Okay. I think its recording is on. Yeah, fine. See, so the question is based on something very similar to this, right? So last time we saw a retaining wall, which is spanning for about 5.45 meters from the foundation level to the top level where the slab is connecting and acting as a rigid pin support. So in this, we are not taking as a cantilever connection wall. We are assuming it to be simply supported with two pin supports, one at the foundation, one at the slab level edge connecting. Now, in this question, we had a different height of the retaining wall, which is about 6.4 meters, I suppose, right? That's one change. Second thing is the concrete grade is M30, that's fine. And the steel grade, I gave it as 500 MPa, FE 500 instead of 550. Okay. So for the yield stress, we need to use 500. Okay. FY. That is also clearly mentioned in the question. Now coming to the loading, there are two things you need to do. First thing is find the bending moment, right? And come up with a cross section. You decide your thickness. You decide your reinforcement bars, the vertical reinforcement bars, which will be in tension while bending. Okay. I wanted that reinforcement bar and spacing only, right? So that cross section design is what is required. So once you decide a cross section, find the capacity of the cross section in terms of the moment carrying capacity, and you compare it with your demand moment. That's it. It's as simple as that. Okay. So in order to find the bending moment for a simply supported member, it's a pin-pin connection. So the formula is WL squared by 8. If you're not written down last time, please write it down right now and arrive at your numbers and see what happens. Okay. So WL squared by 8. Now, in order to get WL squared by 8, we need the L and W, right? Now, L is what? The spanning length, which is 6.4 meters in the current question. Right. Now, how do we arrive at W? I told the loads are, in this case, only two cases. One is the surcharge load and the soil. Now, what is the soil load, which is the soil that is retained, right? The retaining height, which is the same height. So no, the soil load is a triangular lateral force that is coming on the retaining wall. Okay. Now, since it's a triangular, you look at how they have arrived at. As I told you, what is the unit weight of the soil? It's 20 kilonewton per meter cube, right? So that's the density or unit weight of the soil. Now for the triangular distribution is it's half into your 20 is your pressure, the maximum pressure at the base, right? Into height. Now height in our case is 6.4, right? Now you get an answer in your case could be different, right? Now that's per kilonewton per meter square. Since you have multiplied already by the height. Now on it was already density was in terms of meter cube. When you multiply with one linear distance, it converts into kilonewton per meter square. Now, the formula and bending moment simply supported case is WL squared by 8, where W is in terms of kilonewton per meter. It's uniformly distributed load, right? Now, how do we convert this triangular load into uniformly distributed load? And I have told you, just assume it's a rectangle and again, put a half of it, like reduce the intensity by half, then you'll get something like a UDL, right? Uniformly distributed load. Now, you have to take, in order to convert into kilonewton per meter, that is the UDL load, distributed load per running meter, right? Per running meter. So what is the total running meter we have, which is the span. Now, in order to convert that, take 1 meter length in the other direction, right? So I'm just assuming per meter width or something, right? So it's just that, like that's the conversion that we're doing. Now you have one value from that. The second thing is the surcharge load. Again, the surcharge load is nothing but I told you it's 500 mm depth is the surcharge. Surcharge is something on top of the soil, above the retained height of the soil. There could be an additional load. Okay, it could be again an additional soil that is put, or some other sort of dumping could be there. So the height is 500 mm, so that's 0.5 into unit weight of soil. Again, that you get into in terms of kilonewton per meter square. In order to convert into kilonewton per meter, multiply by 1 meter. We are assuming the calculations for 1 meter width, right? That's it. Now there is no passive soil pressure in the current case, so you can neglect that. Now you add these two loads, and you get the total value, which is W. So WL squared by 8 multiply, you'll get a bending moment, demand bending moment. Fine. Okay. Once you do that, you need to now design your cross section. So in order to design your cross section, you start with some wall thickness. So last time it was for around 5.4 meters height. Your wall thickness assumed was 350, right? Now you can do a judgmental calculation and come up with something like a wall thickness of 400 or 450, right? Once you decide that, and you start assuming what sort of reinforcement bars you're going to give. Say, for example, you're going to give 20 diameters reinforcement bar, vertical bar, and spaced at 150 mm center to center, or 100 mm, or 250 mm center to center. Now, in per meter width, how many bars, such bars would be placed, right? It depends on the spacing. You find the number of bars spaced. It could be 6 bars or 7 bars per meter width. Now find the total area, cross-sectional area of the rebars. You assume a 20 mm diameter rebar, right? So 5 by 4 into 20 square, that is the cross-sectional area of a single rebar multiplied by number of rebars. You get that. That is AST. Let me go to the question. Yeah. Now here. So this is now we are in the stage of second stage, which is like finding the capacity of the section that we are assuming, right? So AST is the total area of the rebars. Fy is the yield strength of the rebar. In this case, it's Fe 500. So we have to take 500 Newton per mm square. Now 0.87 is the material safety factor, right? Into D. Now D, as it's again I've given in the question, from distance from the center of the vertical reinforcement to the edge of the wall section, right? That is your D, your effective lever arm. So you know you are assuming a 450 mm thick wall, for example. At the edge, it's from the edge where is the center of the vertical reinforcement, right? So in order to find that, what we do 450 minus, we need to provide cover for the retaining wall, right? It could be 50 mm cover. 50 minus, you will have tie bars, horizontal bars, running around. So assuming 12 mm diameter tie bars or something. So minus that, minus half of the diameter of the vertical rebars that you can. So 450 minus these distances or spaces would give you the effectivity.
Guru,
Yeah.
if possible, can we solve this numerical step by step or something so that we can write along with you or something to understand?
Okay, sure. So let's go. I'll open my.
Thank you. Thank you so much.
Okay, it's a simple case. Now I'm taking the foundation is somewhere here, right? So assuming it to be a pinned thing. And my slab is somewhere over here. So I'm again taking this as a pinned connection. I told the cantilever, sorry, the retaining wall height, the height for which the soil to be retained is. It could be anything. In this case, it's 6.4 meters. Yeah. Okay. Now, WL square by 8 is the bending moment for simply supported members or a simple beam with a two pin connection, right? So I'm going to take this. This is my demand moment. Okay, we need to find this particular thing. Now here L is, we know, 6.4 meters. W is in terms of kilonewton per meter. So this is uniformly distributed load. Okay, that's where the formula comes from. For uniformly varying load, UVL, which is a triangular distribution, the formula is different. Now, this W square L square by 8 is a very simple formula. That's why, like you can always remember this. You can come from uniformly distributed load, right? Now, what's our loading is like? One thing is the main soil to be retained. It puts a lateral pressure called active earth pressure on the retaining wall, right? So I suppose this wall is retaining the soil, right? I'll just mark it so that there's something like soil over here. Right? Now it is going to exert a pressure. That will be a triangular distribution because the more the depth and the more will be the pressure, right? So that's the thing with the pressure head that we assume in water forces calculation and things like that. Now the unit weight of soil is 20 kilonewton per meter cube. That's at the base. Now, in order to find the total intensity of this particular loading, the area of this triangle is half into base into height, right? Half into base value is 20 into height is 6.4 meters. Right. So that is equal to, what is the value, guys? I don't have a calculator with me. Can someone please tell? It's 10, I think 64. Yeah. 64 kilonewton. The units, you always be careful with the units. So kilonewton per meter squared. Now, so this is, we are looking at the triangle in a single infinitesimal space, right? Distance. So I'm going to assume it for a meter width. Imagine the wall will be running, right? It would be covering for a certain distance. Imagine per meter width, we are just calculating for that per meter distance of the wall, right? So I'm going to multiply by 1 meter. So that's 64 kilonewton per meter. Now it's a UVL, uniformly varying load, and the intensity is maximum at the base, right? The formula is for a uniformly distributed load. You guys remember, like, how do we represent uniformly distributed load? Something like this, right? Against a uniformly varying load, something like this. Now, so I want to convert into a simple case, which so that we can use it in this formula. So what I'm doing, I'm going to assume this to be a uniformly distributed load, like using a pseudo diagram, right? Like an overall rectangle. Now, in order to find this overall rectangle, and assuming it should be it's uniformly distributed everywhere, I'm just going to take half of this value, right? And assume it's going to act. You're getting my point. So act uniformly over here, everything. Now forget the top portion. Right. So a triangular load, I'm just converting into UDL, right? This particular thing that I drew right now. By taking half of its intensity, which I'm thinking it could be applied everywhere. Okay, that's the basic funda I'm taking. So half of that, it's 32 kilonewton per meter uniformly distributed load instead of uniformly varying load, which had a maximum intensity at its bottom, right? For simplicity purpose. Okay, this is one of the load, one of the UDL. Second thing, UDL was the surcharge load. Back to the question, surcharge load of unit weight of this 20 kilonewton per meter cube, and the depth for which the surcharge is something additionally put on top. It could be anything. So I'm taking a material which is 20 kilonewton per meter cube density material, which could be filled for half a meter depth. Now that is not uniformly varying. It is something on the top which exerts a uniform pressure, right, on the wall, right? Because it's just there. It's not the soil below, it's something on the top. So that is load number 2. In order to go to that, let's clear up some space. So that's 20 kilonewton per meter cube, right? Into the height of the portion was like 0.5 meters. That's 10. 10 kilonewton per meter square. Again, this is for a per meter width, multiply by 1, it's the same quantum you'll be getting. So that's 10 kilonewton per meter. This is load number 2, the UDL number 2. Add 1 plus 2 will give you the total UDL. It's 42 kilonewton per meter. Right. Okay. Now this is W. Right. So W multiplied by 6.4 meter squared divided by L, you will get the demand moment, the demand bending moment. Right. So this is the kind of bending, right? We are targeting this moment. Now tell me what is the value you're getting? WL square by 8. Guys, someone please just tap it in the calculator and let me know.
215.04.
215.04.
04.
Okay, so it's 215. I'm just taking 215.
Yeah.
What is the unit? What is the unit? Hi, one just answer the quantity. What is the unit, please?
Kilonewton meter.
Yeah. Okay, perfect. Kilonewton meter. Now let's remember, bending moment should be in terms of force into distance. So it should be Newton meter, Newton mm, or kilonewton meter. So from that you can always reverse calculate, what you need to be putting in the formula. Now WL square it would give you meter squared, and W should be in terms of kilonewton per meter. Okay, so meter in the denominator gets cancelled out, and you have a numerator 1 meter remaining in that. So kilonewton is already there, and this is a unitless number, 8. So we are getting the final units kilonewton per meter. That's you can remember checkpoints like this always. Now this is our demand. Now we need to design the cross section to meet this to have a capacity which is equal or more than this, right? As simple as that. Usually, we need to target something more than this. Before, one of the things, like I did not take the factor of safety, like material load factor, right? This is the load value as such. We should be having a factor of safety. So multiply by, sorry, a load factor 1.5. So 215 into 1.5. This is your final factored load, bending moment. That's 322.5. Okay. Guys, tell me what tools do other lecturers or teachers use in order to, write something and show to you? I'm finding writing on paint is very difficult. Does anybody use any other tool?
Yeah, last sem Bhargav used to use Revu.
Oh, Revu. Okay, Bluebeam Revu. You can type on it, right? Yeah. Okay. So your final factored bending moment was 322.5 kilonewton meter. I just multiplied by 1.5 the load factor, right? For this, we need to design a section. Now, what do I do? From my engineering judgment, I'm going to take an assumption section, which could be, closely working around that, and like a starting section. Later on, we can optimize. Like once we do that, you will know, what do you mean by optimizing. Now, last time we saw this particular section, which was like for 5.5 meters. somebody took 350 and they used to T20 bars at 150 spacing, right? And it turned out to be okay. Let's see what we can assume. So, and I'm looking at the plan cross section. Okay. Wall. Okay, this is for 1 meter. Now, this is the phase where the rebars are facing tension. So, I mean, the tension side of the wall. Okay, like this side is where you have the force, the active soil pressure coming in. So you'll have tension here and you'll have compression on this side. So I'm just, both of the both faces needs to be reinforced, but the other side needs to be just reinforced for minimal reinforcement. It is not facing any tension, right? Because only from one side the soil is there. So the important side, where the tension side is, there we need to design for the demand, how much we need to meet. The other side could be minimal reinforcement. Now the question was finding this thickness and the reinforcement diameter and spacing. That's it. Okay. Once you do that, the other things you can put minimal reinforcement. What do you mean minimal reinforcement? Cross section of a member, any reinforced concrete section should have some reinforcement. That is given in terms of percentage. If you refer IS 456 code, it gives you, it could be in like 0.6 percentage of the cross section of that particular shape, or 0.8 percentage of the cross section of the particular shape, right? So, but first we'll focus on the important parameter, which is the overall thickness. It's X over here, and what are the reinforcement bar sizes. Now let's take 450 mm thick wall. Okay, I'm just assuming 450 mm thick wall. Okay, and which is X here. Let's take, instead of T20, like take 25 mm diameter rebar. Okay, 25 mm. So T25 at say 150 mm spaced center to center. Now, in 1 meter, how many such bars can be placed? This we are doing in order to find out the total area of the rebars, right? How many rebars are there? So how many cross sections are there? I'm going to add up all the areas of those resisting rebars. That is the one which is experiencing the force. So all the rest of the concrete is not in that zone, in the tension zone, is not contributing to anything, right? There are two formulas. One thing is to find the capacity using this reinforcement bars and the forces and the stresses that they are experiencing. Okay, that's where this formula comes in. 0.87 into Fy, the yield stress of the rebar, into total area of the rebars, right? Total cross section area of the rebars, into D. D is the lever arm. So, which is nothing but the space, the distance between center of this rebar line to this edge of concrete. That is your D. Okay. So tell me how many rebars can be stacked within this 1 meter width. So, someone please tell me some number. So in a 1 meter space, which is 1000 mm, so divided by number of spacing plus 1, right? Something around like 7 rebars I can place, right? 7 rebars, 7 numbers. So that into what is the area of the individual rebar? 5/4 into 25 squared. Okay, this is the total AST. What is that value? Someone give me an answer, please. 7 into 5/4 divided, pi by 4 into 25 square. Guys, come on, give me a value.
It's 490.87.
That's for one single rebar, right? Into 7, into 7.
3436.11.
Okay, 3436.11. And this is the total AST, so it is in mm, so mm squared. Okay, that is area. Now what's the second thing in the formula? We need Fy. Fy, we know we are taking Fe 500 bar, so Fy is equal to 500, which is already in Newton per mm squared. Right. So that value we know. What is the other value we need? Fy, we have AST B.Arch 0.87 is the material safety factor into D. Now, take a cover distance of concrete cover, right? So there will be horizontal bar running, right, on the outer face. So cover to that rebar is 50 mm. Where can I write? Cover to that rebar is 50 mm. Let's say cover is equal to 50. And this horizontal rebar, the running rebar, I'm going to make it a 12 diameter rebar, or 16 mm diameter rebar, something minimal. So let's just take 12. So that is there. So 12 mm horizontal rebars, like let's write horizontal. Now, and the center of this main vertical rebar, which is 25 divided by 2. So we should take 450 overall depth minus cover. So 450 minus 50 minus 12, which is the horizontal rebar that is running on the outer layer, minus half of the main bar diameter. What is that value? That will be our D. What is D? Guys, what is D?
375.5.
Okay, great. 375.5. Yeah. So you got all the numbers to be plugged in this equation. 0.87 multiplied by Fy, which is 500, multiplied by AST. AST was 3436.11 multiplied by D. Right. D is 375.5. Now, everything is in distances are in mm and the force is in Newton, right? Remember that. So you'll get a very big number. So in order to convert into kilonewton and meter and compare it with your design moment, right? So what we do? We divide this in big number that you get the answer in your calculator by 10 to the power 6. 10 to the power 3 for converting from Newton to kilonewton, and 10 power 3 again for mm to meter. So 10 power 6. So divide by 10 power 6. You will get, what are you getting, guys? So what is the final capacity you're getting? Let's call it MU, ultimate capacity. Give me an answer. Hello. Point 0.87 into 500 into 3436.11 into 375.5. You'll get a very big number divided by 10 power 6. What is the final number you get? Hello. Someone was answering, right? Guys. Am I audible? Hello.
Yes, we are. You're sorry.
Yeah. So what is that number you're getting?
561 point something.
Yeah. Okay, great.
561.262.
Yeah, 561.26. This is again kilonewton meter. So this is our capacity of the section that we assumed. So this is our design. Now the demand was 322.5 kilonewton meter. We are surely exceeding the demand, right? That's good. That's how we need to design our. Now, how much we are exceeding, that's on us, right? So a better designer, what you would do, you would optimize. What do you mean by optimize? Yeah, he might reduce the concrete entire wall thickness or decrease the number of rebars. So instead of 150 mm spacing, what I would do is I would keep it at 225 mm. You know, every 25 mm increase, because 25 mm convert to be 1 inch, and it's very easy on the site to move something like 1 inch or something, right? Instead of 5 mm, 10 mm, right? So you need to have some practical considerations also. Let's jump 25 mm, right? Instead of 150, go for 175 mm spacing, 200 mm spacing, or 225, 300, 250, 275, something of that range. And when you increase the spacing, what happens is essentially you're reducing the number of bars, right, within that 1 meter. So you're driving towards economy. So that way we can do. And what we will do, we'll end up with, instead of 7 bars, when you increase the spacing to 300 or 250, you will end up with 4 bars or 3 bars. So overall, you are reducing the number of rebars, right? And again, now you're checking the capacity of this section, how it turns out to be. That is one way of going about. The second thing is reducing the entire wall thickness. Instead of 450 mm, try to do it with 425 mm or 400 mm and see what's the effect, right? What will happen in this case? Your D will only reduce, right? If you are changing only the wall thickness and not changing anything else. Now you have two things: you reduce the concrete section size, or you reduce the steel size, or reduce the steel diameter for the same spacing, or as I told in the first case, increase the spacing so that you have lesser number of bars, or do both. Try for T20 with 125 mm spacing. Don't go below 100 mm spacing. Okay. Because you need to pour concrete also, right? The concrete aggregate size is something, 20 mm aggregates could be there, or 40 mm aggregates could be there. That should pour into the congested reinforcement that should flow into. So you need some rebar spacing minimal. So practically 100 mm would be the minimum rebar spacing people would try to maintain. So the concrete flows and you form the member that you want. You're going to, create a member, right? You are going to create a concrete section, and that should be uniform. It should not be having any voids. It should not be having any gaps where the concrete has not filled. Okay. So that's about it. You're getting the overall idea, right? So in this particular case, the starting section that we assumed and the capacity it has in comparison with the demand. So there's something called demand by capacity ratio, right? Let's see. So 322.5 is my demand divided by the capacity that we came up with is 561.26. So that is around 0.57. So there is room for increasing. What it says is I'm utilizing my section for about 57%, right? 0.57. When you tend towards 1, that's what a very good design is. Because your capacity is such that it is not exceeding 1, because your capacity should always be higher than the demand, but it is something tending towards the demand value, it's something which is very near. So if it's like 80% or 90%, if I have my capacity, say 350 kilonewton meter instead of 561, okay, 350. So let's compare that. 322.5 divided by 350, that's 0.92, right? So it's about 92%. Utilizing something for the forces that is going to experience, right? The capacity is good, but it's not very high, so that it's not uneconomical. Hope you guys are getting that point. So this is what is optimizing is, so for one member that we do it, there's another way of optimizing it in order to know really if W(h) by 8 is the formula to be used. So here for preliminary calculation, I told you, let's take a simple case example. But in reality, you could have some other slab joining here and there, right? That could give some sort of supports. So your entire bending moment could be, when you do an analysis in the model, in a computer simulated model, it could be something less than W(h) by 8 value. So for that, actual true demand, or then we can again reduce the cross section size and the rebar diameters to optimize it. So one is analyzing properly. So optimizing and analyzing in a way, you do a perfect near perfect analysis, and you design something to meet that demand. Okay, that too not way off. Your capacity should be something near, but on a higher range, say 10%, 15% higher than your demand. Okay, so that is what you call structural optimization. So as I told you, for one particular member, you have so many members in your building, right? And so many different structural components, beams, columns, raft, pile caps, so many things. So that's what it does. A lot of reiterations happens, and an experienced designer would tell how to analyze and arrive at a very economical members, and which also stands and supports all the load it is going to experience in its lifetime, the building's lifetime. Okay, great. Hope you guys understood, right? Yeah, any question on this numerical example? Okay, I suppose no, now it's hello.
Yeah, after finding the MU, we found what did we find? Sorry, the reinforcement number.
Yeah.
Okay.
Now, what was your question?
What was the next step after finding the MUs? Was it finding the number of reinforcements?
Right, okay. Your question was, so we understood, we came up with the section, right? We decided what thickness it should be and what rebars I'm placing, and I found the capacity of that section. So if this is way too higher than my demand, what I'm going to do is I'm going to change the diameter on the spacing, or or reduce the cross section and see what happens after this. Is final detailing would be what essentially we saw right now was we just designed this vertical tension rebars. Okay, so there's so we need to just put a minimal rebar on this side, this face as well. Okay, similarly, there is a moment, a cantilever bending moment, which is experienced by this particular member here and this particular member here. So for all the cross section, whatever the forces it's coming, whatever the bending moments it is experiencing, we need to figure out what is the rebar that we need to put. Okay, that is one. Second thing is, this is bending moment calculation. There's something called shear force, right? What is the shear that is coming at each place? What is the maximum shear? Is our capacity at that particular zone is meeting the shear or not? So you figure out these reinforcements to be put, including vertical and horizontal and all those detailing. Then we need to mark in our drawing something like this, right? That you see on the right side. So you see the vertical bars running, and you need to give this markups or how to detail to a draftsman. So CAD draftsman or someone could be, he takes inputs from the designer and marks and then creates this detailed diagrams. Okay, so here then again somebody has to mark and say, okay, this is what they are putting 16 mm diameter bars at 220 mm spacing. Okay, and the horizontal bars, what are they? And on this side, what is the vertical and horizontal? And again here, and the toe and the heel, and what should be the length also? We should mark it and show how much is the actual length we need to give. So all this detail, everything will be read by a site execution person, and it will be detailed and placed in such a way. So it is like your drawings are your language that is spoken through the paper, right? You're instructing someone to place all this on all the thicknesses. So here they are specifying 420 mm thick here. Here it's top 200 mm thick. So bottom here. So every detail will be read by someone and it will be executed on site. So we need to do detailed diagram and check it if it's all as per your intention, as per your design, and release it so people can execute work. Okay. Any other questions, guys? You understood, right? The overall design principle. and how the detailing is also needs to be done. No, we did not go into the specifics of detailing. The point we need to understand is everything that you draw on what do you call, they call it good for construction drawings, GFC drawings. It's very important. We need to make sure the details are well read. It could be well read, and there will be no ambiguity, and it could be completely followed on the site, because nobody checks the design at the site. Nah? They just assume whatever comes on the drawing is perfect, and they just try to follow in the drawing. Any other questions? Okay, so if not, I looked at all your assignments. I have some comments and queries before I can, start grading your assignments based on your submissions. So one thing is, overall, every group has done a lot of efforts in like creating this. I suppose it's not only for theory of structures class, because it comes from your theory. I mean the studio that you are attending, and some of you guys have well expanded the structural part of the building in your case study, and some of you have not done so much or not put so much effort into explaining the case, like the structural aspects of the building. So please, if you have not done such analysis and such presentation, please do add it and resubmit. Okay. Just don't submit something that you have already submitted to the other studio class. Okay. Now I was going through the submissions, and whatever I found interesting or where I had questions, I would like to ask you guys, and so that like the other members, like of this class, everybody also learns from this particular thing. Okay. So this one, let me close this tab. Okay. This is in Lebanon, the terraces. I had a question from this particular one. Bubble deck slab. Yeah. Okay. The team who created this presentation, please do answer for this. I just have a basic doubt. I think some other buildings also use the system, voided slab or bubble deck slab. Basically, it's a deck slab or a slab, which is they're not completely covering with only concrete. They are putting some plastic, like this bubbles or voids artificially. They're putting particular thing so that the rest of the space only could be occupied by concrete. Basically, they're reducing the weight of the entire slab, and about 35% it could reduce. Now, the team for this particular project who had done this case study, tell me, apart from reducing the weight of this particular slab, there could be other ways to reduce the slab weight also. Why a bubble deck concept, or why the slab is chosen? Janvi, Amit, and Vishaka. Anyone? You guys are here, right? Amit is here, Janvi, and Vishaka. Amit, can you please represent your team?
Hello. Hello.
Yeah, Amit.
Yeah, I think maybe because it's a very tall structure and it works on a module system. So each floor has same alignment, but with different orientations of the rooms. So it's a 27-story building. So to reduce the waste, they might have opt for this bubble decking system.
Okay, yeah. So obviously, yes, reducing the weight, dead load is one of the things. Now we can do by other methods, right? What we can do instead of the what do you call the wider slab, instead of putting in this plastic bubbles, they can just remove. They can reduce the cross-sectional depth itself, right? You could just have a 25 mm, 50 mm thick slab instead of, if you add this void and pour concrete into it, the overall depth is something which is much more. Like, why can't they just avoid everything above this concrete layer on the top? Like, just avoid this slab, I mean, the bubbles and the depth of the concrete that the bubbles layer would occupy. I mean, why didn't they just go for a thinner slab?
What I think is it must be because of the services part, because of the thickness of the slab they were able to insert those radiant heating system tubes inside the slab, which was helpful in maintaining the temperature in their interiors of the building. So if the what radiant heating system was, they absorb thermal energy, and it works on electromagnetic waves. So if the interiors are warm, it used to absorb the heat from the interiors, and vice versa. So maybe because of that, they have created those voids so that they can insert those tubes with the and tie up with the mesh. We
So
didn't
Amit,
included the services part in this because it was like a technical subject. That's why.
okay, Amit, so what happens in other buildings? Where do they run the cooling system and the services? Amit?
Yes,
Yeah, yeah. Thing is, there are other many buildings which are done without this wider slab, where they have their services perfectly running, not through the slab, just below the slab, and it could be hidden by false ceiling. And you have some steel beams where they have web penetrations through which some services runs and all that. Now this is not just to put in the services inside the slab, right? That's not the point of a wider slab thing. They turned out to be an advantage and that they can use it for that purpose. Okay, why I'm repeatedly coming to this question is wider slab reduces the structural dead weight. Now, how it's possible? Yeah, it's reduces because obviously you're not putting in concrete everywhere. You have voids inside them. Now, how does it work? Do you know, like, I mean, can you please explain how it's possible using a wider slab instead of a solid slab structurally? Structurally, you don't see any weakness. There are other groups also, like I think somewhere I saw wider slab system. And okay, the case study on Lloyd's building. I think guys, whoever has done this and needs to add some further explanations on the structure, because it's I think single or 2 pages you have added, right?
Yeah, but this is all that we were getting from the. We tried contacting uh, the architect, but this is all that we were getting from the internet. We didn't get a revert.
Okay, it has some shear walls and there are some columns, and
Mhm.
what happens? So how is the lateral system like? And you have the floor plates and you don't have any outriggers or connecting members, right?
Uh, just 1 second. I, 1 second. The person doing the structure part of it was.
So you have different person among your team covering structure part.
We had done the initial research and everything together. Then we split. And,
Okay. Okay. See guys, like everybody needs to
but
be aware about
yeah.
everything. Okay. So I'm just trying to extend your learning to other group members also. Okay. Please do help in that regard.
Yeah. But we'll look into the if there's any other information that we
Yeah.
get.
Okay. Are you satisfied with the overall structural system learning that you had shown here?
Since our this building actually it focuses more on the services uh part, but
Mhm.
since we already had this building for the case study,
Hmm.
uh this is all that we
Yeah.
could get for the struct. This is what we made the precast joineries.
Okay. Okay. So if you have any further questions, please note it down, and maybe we can discuss about that. Like if you're not very
Okay.
sure about what's happening and all. Okay.
Yeah. Yeah.
Right. Okay. So there was somebody else who had voided slab system shown in their case study. I think 2 or 3 other groups had a voided slab system. Guys, answer up. You only did the reports, right? You must be pretty sure knowing if you had a voided slab system mentioned in your report. This was interesting. We'll come back to this. Yeah, here. Group. Why didn't you why didn't you tell me you also used this, right? Riddhi, Shruti, and Adira. Are you guys here? Guys? Yes, Adira is here. Adira? Hello. Anyone from the group can answer? Hi, some response, please. Hello. Okay. Nobody is responding. I don't know why. Okay, so slab system is again you have a wider slab system in this case. So let me tell you, where my question is coming from. Just for a better understanding, why this wider slab system is not used everywhere, because it's in the research stages, and so see. It's not yet, like uniformly designed, like everywhere the international codes in each countries haven't got anything solid on it. So a general uh, building construction team or design team would not be following something because there's no codal references for that yet. There are some references, there could be in some other international codes, but as in India, it's not yet there. The research is still ongoing. So you take some, for example, any cross section of a slab, okay? Or deep. Now any slab is going to bend and it's going to bend down. The tension is going to be somewhere here, right? So in order to carry the tension forces, the concrete is very weak in tension. It is assumed to be, yeah, cracked. So only the rebars will be carrying the main tension, right? So if this is the D. Now what happens is, why I told you now, only these reinforcements are carrying, and there's something called neutral axis, right? NA. Now above you have compression and below you have tension. Wherever is tension, you are essentially what is happening is in the tension zone, the concrete is not contributing anything at all. Only the steel reinforcement bars are experiencing the force, the tension, and that is what is carrying. Anything above neutral axis only, your concrete is effective. What I mean by effective is your concrete is stressed here, okay, because it's in compression.
Hello.
Yeah.
Yeah, sorry, I had a connection problem. You were asking about our.
Yes,
Yeah.
Adira. So you had also chosen a wider slab. I mean, in your case study, there was a wider slab system mentioned.
Yeah, we had a Kobiax system in our in our
Yeah.
building.
Okay. So can you please tell me how it's working apart from the reduction in the dead load that is contributing and some other functionalities? The basic principle behind the structural principle behind water slab system.
So, like when we researched, what was written was that the load is, there is reinforcement at the bottom and on top of these, like these voids and all that. So the reinforcement and like the load is getting transferred into the, it will be taken up by this reinforcement, and then these plastic void fillers are just there so that less amount of concrete is used. But the way the load gets transferred is the same only. I mean, that's what.
Okay, yeah, you're coming somewhere close. That's good. So what happens is we need this effective structural depth. Okay, so if there is very less depth, what happens is you are having a very thin slab in design. So you might have to put lot many rebars. When you have an increased structural depth, and what happens is your forces right at the outermost edges reduces
Yeah.
for the same load that is coming. Like there's a same fixed load that is coming from the top, and you have a thicker or a deeper cross section, your bending forces, bending stresses is reduced. Okay, so we need to maintain this height or depth of the section. But the concrete, most of it is useless. I told you, below the neutral axis, it's kind of useless. It's not experience. It's not contributing to anything. So essentially, we are putting in so much concrete, which has cement and aggregates and sand. And when cement produces so much carbon dioxide, there's this carbon footprint also. The idea was to reduce the dead concrete, like whatever which is not used by some other means, and also maintain a structural depth. Okay, so they thought, okay, let's fill it up with some lightweight material, and that material should have some properties where it can bond with the surrounding concrete, whichever is put, and it should not undergo any other drastic, shouldn't cause any other damages to our slab system. And your overall depth is also very important for fire rating. Suppose you have something, a slab which is like very thin. You will have what you will have, like for example, instead of the same slab above, you find something very thin. It could be like 50 mm or something. First of all, it's going to bend deflect so much. Okay. Second thing is fire rating. Now, if it starts to experience fire because of something, it needs to stand for a few hours. There's something called 1 hour fire rating, 2 hour fire rating, 3 or 4. So buildings, most of the important buildings are designed for 4-hour fire rating. At least for the vertical members, your column, shear walls, and all those things should stand for 4 hours of fire, so that within that 4 hours, any fire extinguishing service can come or people can escape out. So your main members should not collapse. Okay, so the idea is that typically your slabs would be around 2-hour fire rating. So you need a sufficient amount of thickness. It can stand for 2 hours. So this 50 mm thick now, it won't be standing for that much, because the fire can reach the reinforcement bars inside very quickly in some minutes itself. And when the reinforcement touches its some critical temperature, it is going to yield so much, and it's going to lose its strength actually. So it's going to bend and deflect and damage and fall down. So in order to address that also, in order to address the deflection, in order to address the fire rating, in order to reduce the concrete so that it can be put somewhere where it is better utilized, the idea was to go for water system. Now they have uniaxial bending slabs, which is bending, in one direction, and there are biaxial bending slabs. So research is still going on, and people are trying to use some pre-strand, pre-stressing strands also in addition to the wider slab to enhance the slab system. Okay. So that's something I wanted to tell you because it's not common everywhere, because it is not yet the learning has not yet been crystallized, and we can use it everywhere in all the countries because we need to follow some code systems and requirements. Can be done as an experimental basis, but it's still not uniformly applied everywhere. Okay. Okay, so this particular case study by Manasi, Akansha, and Nikhil. I had one question. Okay, you had talked about how the external geometry has been designed. Where is the design methodology coming from? Okay. The glazings, external facade and all. Okay, so how the diagram is transferring the load. I just wanted to know, okay, you have a central core system, which is again made up of steel concrete composite buildings, and that core runs from bottom to up. That is the primary structural system. The secondary is the tie beams. Tie beams, I suppose, which is connecting the outermost columns to the central core. And tertiary is the diagrid. The diagrid is also carrying the vertical loads and transferring it to the bottom. Now here, I have a question. The rigid frame made up of moment connected steel. Okay, all this beam column, the steel beam and steel column are rigidly connected. Okay, they have a fixed connection. Fine. Second thing is it transfers vertical load to tie beams. How is this happening? How is this column vertical load is transferred to the tie beam? Can you please explain? Anyone from the team?
Yeah, like I'm not very sure, but I think the columns and the beams which are present on like in the core, the frame, like we did not read anything about it, but we like analyzed it that maybe the column which is transferring the vertical load that goes onto the beam and the beam is connected to the tie beam. So then like that, like, I'm not sure.
Okay, the thing is this vertical load, you find some columns here, right? Below.
Yeah, the core is from the ground floor till the 40th floor, the upper floor.
So won't this vertical load just drop down to the column below and just go to the foundation?
Yeah, but I think the tie beam is then to connect the core and the digrid so that it does not sway.
Correct, exactly. So your digrid is a separate entity, which is like running around, and your core is in the center. So that needs to be. It is something similar to a system, a deep beam or an outrigger. Okay,
Yeah.
something of that only. So unless and until this is slanted and it's sloping, there won't be any force transfer, the vertical force transfer to this what do you call as tie beams. The vertical load transfer just goes below. There are columns here. There's no transfer girder or something where that carries the load and transfers to where the transfer girder is supported. No, this is like it goes down. Now these tie beams are connecting the core to the outermost diagram. Okay. So now the lateral forces are the ones that will be transferred between the tie grid and your core. Okay. Is that clear?
Okay. Yes.
Yeah,
Yes.
that please do change it, and that's what is happening. Okay.
Yeah. Okay.
Thanks. Okay, here was an interesting case. Yeah. Okay, this case study is on Portia downtown, Singapore. Okay, which team has worked on this? There is no name here. The team who has worked on this case study, can you please speak up?
Yeah. It's Dalika, Akshit, and Risha. We3 work.
Okay, good. I was just looking at this foundation analysis here. Okay, so this soil condition is shown for, and the foundation which has been done for all these surrounding buildings, right? That is what is shown here.
Yes, yes.
Okay, interesting. So here we have a soil profile below. What happens here is, guys, the rest of the class, please do pay attention here. So there's number of buildings in this neighborhood, and what are the kind of foundations that has happened is being listed here. So building number 1, it's something here, the International Plaza, and that has a rafter. kind of foundation. So that's shown in your raft. Okay. I don't know what is the height of this building or something, but let's see figuratively, all these models can be compared. I don't know if it's like scaled too much, varying from each other, but let's assume it can be compared. Now the second one, they have a Kazon foundation. Kazon is something similar to a pile foundation where you undergo, you come across some water or moisture or some sort of, like some water body below. Okay. And building number 3 have what kind of foundation? Board piles. Okay. They have a pile foundation. Now, what's the difference between a board pile and an RC pile? I think boring pile is like it's a precast pile which is like driven from top and then they are inserting it rather than cast in situ piles. Okay. So I think this particular page or this alone, please share it with the entire group and see for the soil profile below what are the different foundations that has happened. So I don't know whether we can read this particular gray shaded portion. What is it standing? Where's the water table? Is water table shown here?
Not exactly, but then this whole area is situated next to like the water. So, but the table is not shown particularly, the water table in the soil.
Okay. Okay. So guys, have a look at this thing and try to figure out, what's happening. So what are the different buildings? So on a more or less, when we encountering a similar soil system below, the building foundation design should be responding to that in a similar way as well. Okay, let's just see if it is happening in all these building foundation designs.
Yes, we'll look.
Did you find anything interesting here you want to share with the class? Like something that you came across?
No, so exactly what we did was we didn't have any much information on the foundation of our own building. So we tried looking at the buildings of the surroundings. So we found a paper which actually was analyzing that part of it. So from here we found out that the region that our building and the other neighboring buildings lie in is like a alluvium soil like type, the soil that is there, the condition, and it's also next to the ocean. So most of the like the buildings here, they used pile, but then they go like really deep inside, maybe because of the height. So all the buildings surrounding are like really tall. They all are almost high-rise structures. And from that, we concluded that the nearest building to our building was like the third one, which is the CPF building. So we assumed that our building would also sort of have like a pile foundation, but again, the height of the building would be like a factor in which the depth of the foundation is also determined. But we were actually quite sure then that it's actually like a pile foundation than any other foundation. So that was the whole analysis we did.
What was the depth of the building that you took, the foundation depth it was?
So we didn't give a specific depth of the foundation for our building because we weren't sure of how much it could be. We didn't give a range. But assuming from the thing that is given here, I think it might be around 50 to 60 meters.
Okay. The question on this. Okay. The people who, the group who presented the shard building, please send me a downloadable copy also. You had mentioned, yes, there are some GIFs which are like, which cannot be shared in a PDF, but please do share me the PDF because I've seen this things. So I'd like to have a PDF because I'm not able to zoom in and see.
Yeah, we'll do that.
Okay, great. And here you had mentioned the floor system to be somewhere like castellated beams, right? Is it called castellated beams?
Yeah, so like till level 37, it's castellated beams, and then after that, it's a post-tension concrete slab.
So castellated beam, what is the depth of the beam they mentioned? Is this
It's a 500 mm deep beam.
it's
Well,
500?
300
So
mm.
okay. I just wanted to make one more clarification here. Is see this 500 mm, 600 mm, up to 600 mm. It's available readily. So in I think most of the countries, right? So they don't have to actually go for castellated beam. So castellated beam is something. It is something like this. What happens is they cut across the entire beam in a particular section. It could be hexagonal section. Okay, they want to make an hexagonal section. What they do is they cut a hat section like profile throughout, and they detach these two parts, move it a little bit, and make one sit on top of each other, and again build it. There's this cutting, moving, attaching, and building. Now, this kind of formation is called a castellated beam. Essentially, what happens is when you run out of beam depth, I think this became very famous during the World War times, like during First World War and Second World War time. They had massive production. There could be a certain amount of depth only that could be rolled in a mill, right? Like it's readily available in the market. So if they wanted to increase the cross-sectional depth, they did this. They cut this, welded it, and now you have an increased structural depth when you do this. And one thing is where this is used where the slab is like spanning for a long distance and it's lightly loaded. You don't have any heavy point loads or like concentrated loads where it can have heavy shear forces somewhere, because obviously then where there is no web area, you don't have web shear resistance, right? So this is like a lightly loaded flow system only would be having this. So if there is heavy shear loads coming in, we might have to add some stiffener plates. Okay, now this is what is called as a castellated beam. So here, look at this example. They want to increase the structural depth much more. So they added some square or rectangle plate members in between the two cut members, and they then welded everything together. Okay, so here, when they're having a 500 mm depth or 300 mm depth things, it's already available. What they're doing essentially is they're making web penetrations, right? So a castellated beam terminology, I don't know why they are used it here, but essentially they have a readily available beam and they're making holes or penetrations in the beam. Okay, you're getting my point.
Yes.
Okay, so if they mention castellated, that was I was curious about it. Why did they mention it castellated? Anyway, this is interesting. Okay. Okay. The John Hancock Center. Here I had a question. Okay, most of you guys would have seen this particular building. It has an exterior exoskeleton like system, and there are some columns inside. And here the team has mentioned the load is distributed from the diagonal bracing to the exterior columns. Yeah, fine. The tower's lateral stiffness, we have lateral force coming in. The primary lateral stiffness is derived from cantilever mode, which is 80% of the lateral sway due to column shortening and only 20% to shear frame effect. Can you guys please explain this so that others can also understand what you mean by the statement? Or I can also help you along with if you're not sure. But if you had added this, and I thought you already know this, I just wanted to know from your side, like what do you exactly understand by this? I think I spoke to the team members before, right?
Yeah, actually, we spoke the 1 week back only.
Right. You had added this like somebody has added this, right? I know you got it. You also learned it. Are you sure you exactly understood what does it mean?
I guess it's like majority of the load is transferred from the X bracings which are there on the exterior. So basically the X bracings, they transfer the load to the columns which are there on the exterior side, and the internal columns are just the gravity load.
Right.
It's like mostly
Right, right. So for your lateral, that's more what you're saying is very true, very right. So what happens is, see, basically you have, see, there are two systems, right? One thing is you have a beam column system. There is a beam and a column system.
Yeah.
When this is undergoing a lateral force, because of the fixed connections between the beam and the columns, it has some resistance. It has some resistance to lateral sway. So this lateral sway resistance. Now, the first thing is a beam column system should be rigidly connected, right? We saw this, like there's a simple frame. The first thing is to rigidly connected, or you have a shear wall, or you have a bracing, which can take. So these are the only way we can make it laterally stable. So there's an increasing order of lateral stability that one thing does. From the ascending order, the first thing is your moment connection or rigidity, frame connection, moment frame, which is effective up to certain point. That is why you see in the tall building methodology, like you would see a simple moment frame would go for about 10 stories or 20-story tall, right? Beyond which, so this can affect, this can reduce the lateral sway, but up to a certain story height, around 20 story or something.
Yeah.
So if you want to go more taller, then we have shear walls in between, which are like very rigid. It's very rigid, obviously. So this lateral sway effect, like reduction by shear wall is much more. So that's why we are able to go something beyond. So I think with the shear wall, you can go up to 40, 50 stories or something like that. So, but you would have seen when you add bracings, which are like massive bracings, as in this particular project. Where is it? Yeah, these are like not small bracings, which is running from like individual column to column or individual floor to floor. These are running across several floors, so that forms a very, very rigid system, and your lateral sway is much more effectively taken by it. Okay, that's how you are able to go much taller. So this moment frame action and the shear wall or the diagonal bracing action there are contributions each byte. You can have a combination of all that. So that's what you had here mentioned explicitly, where the contribution by the diagonal bracing is 80% against the lateral sway, and your shear frame effect, which is nothing but the moment frame effect. That is given by, it is contributing only 20%. Okay, so that's good to learn. Okay, thank you for putting in that. Yeah, so you already have this evolution of tall building systems. Okay. I hope you understood what do you mean by this also. I just don't want to spend so much time here. If you understood, it's good. If not, please do ask me later. Okay, so here, this particular thing also had a good example. What is this building? Lakhtha Center. It's in Russia. Okay, it looks cool. Thing I wanted to show is here. Yeah. See, this is the bending moment diagram of a cantilever. This entire building, when we are seeing as a cantilever, if not for this outriggers, where the core is connecting at several levels. We saw this example in our previous lectures also. The base, the moment at the base, right, due to the cantilever action, it could be this. But what is happening is we have a system which is connecting the core to the outermost places using outriggers. Wherever outriggers are there, you can see essentially reduction in the bending moment. There's a drop here, and there's an increase in bending moment after the next point. There's a drop here. So similarly, corresponding to the outrigger locations, you have so essentially your bending moment. I mean, imagine if you are designing for something like this, the bending moment of this particular scale. Imagine the foundations, right? It needs to be fixed. The kind of forces that is coming there, and you would put large section sizes over there, lot amount of reinforcement bars and all that. So a simple thing, like on something like an outrigger, which is put here. Of course, it occupies some material, but it drastically reduces the overall deflection and also causes less complications in the foundation design. Okay.
Yeah.
Thanks. Okay, guys. So if you had not put so much, time or effort into looking at the structures, because one thing is you're not getting so much information. If that is the case, please do let me know. We will try to, discuss what's happening in this particular system. Okay. So the idea is not submitting what you have submitted already. Please try to get some learning. You can talk to your other friends, groups who are doing some similar buildings and try to understand what's happening. Okay. Yeah. So thank you. We'll meet next Saturday, probably with a new topic that we'll be discussing. Okay. Any questions as of now before we complete today's class?
I actually wanted to ask that should we resubmit the
Yes, if you feel like
like
you need
told us to change the for like our building was the gherkin, so like
correct.
we have changed the thing like
Yeah,
the
that particular slide, where you're showing the load transfer, please
so
do
we'll
change.
like mail it to you again, right?
Yeah, we'll do that.
Okay.
Others, if you'd like to, add some more information about your the structural part of the building, please do add it and submit. Most of it was fine. You had put, like a lot of information. Thank you for that. Others, if you feel like you'd like to add more, please do it. Okay. Any other questions? Okay. So thank you. You had a question?
No.
Okay. Okay, guys. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.